Welcome back to Doc Tensors, everyone. Ready for another deep dive?
Always.
Today we're looking at PBM-VFL, Vertical Federated Learning with Feature and Sample Privacy.
Oh yeah, this is a good one.
This paper is tackling a really interesting problem. How do you build a really powerful AI model if nobody wants to actually share their data?
Yeah, like a classic example, right?
Yeah.
You've got like a bank, a hospital, and an insurance company.
They've all got data about you, but none of them are really going to be super keen on just handing it over to each other.
Exactly. And that's where PBM-VFL comes in, right? It's like a breakthrough because it lets these different organizations collaborate and train a model together without actually having to sacrifice privacy, which is obviously a huge deal.
So we can have our cake and eat it too. Collaborative AI that respects our data.
I like that.
But before we get into how PBM-VFL actually works, maybe you can set the stage a bit. What led to the need for this kind of approach in the first place? Give us a little bit of the history.
All right. So the whole quest for privacy in machine learning, it goes way back. I mean, the early days, people were mostly focusing on things like anonymization, right?
Right.
Like trying to strip away any information that could directly identify someone. But it turned out that that wasn't really enough.
Hell.
I mean, researchers, they're clever, right? They figured out all these ways to re-identify people, especially with all the extra data that we've got floating around online these days.
It's kind of a cat and mouse game, isn't it?
It really is.
Yeah, and I think a really good example of that is that case with the Netflix data.
Oh, yeah.
Where they thought they'd anonymized it.
Right.
But then researchers were able to cross-reference it with public IMDb data.
And just like that.
And figure out who was who.
Exactly. So it just goes to show, right?
Right.
Simple anonymization has its limits.
Big time. So what happened next? What did people start looking at?
So that's when people started to look for, more robust solutions, right? And that's where differential privacy comes in, or DP for short.
Okay. I think you actually explained DP in an earlier episode.
I probably did.
Do you remember that analogy with the coin flip?
Yeah.
Answer a sensitive question. I remember it because it actually really clicked for me.
That's the goal.
Ah.
So DP essentially boils down to adding noise to the data, but you got to do it in a very specific way. And the whole point is to basically make it impossible to tell if any one person's data was actually used in the analysis or not.
So it's like you're adding this layer of plausible deniability.
Yeah, you could say that. And DP's become like a really important tool in this whole field of privacy-preserving machine learning.
So we've got differential privacy for protecting those individual data points. But PBM-VFL, you mentioned earlier, it also uses something called secure multi-party computation.
MPC, yeah.
So how does that come in? What does that do?
Okay, so imagine you and I were trying to calculate something together, but we each have this piece of information that we absolutely don't want to reveal to each other. Right?
Okay, so it's top secret information.
Yeah, top secret. So MPC is kind of like this magic trick. It lets us perform this calculation together without ever actually seeing each other's individual input.
Wow. It's like we can add two numbers together without knowing what either number is.
Exactly.
We just know the sum.
Yeah, we both put our numbers into this kind of black box, and then poof, we only get the final result.
So it's like a mathematical trust fall.
I like that.
Okay, so we've got DP for individual data points, and we've got MPC for secure calculations. But, the paper focuses specifically on vertical federated learning, which is where different parties have different types of data about the same individuals. So how do these pieces all come together to address that particular challenge?
All right, so remember that bank, hospital, insurance example?
Yeah.
They each have a vertical slice of data about you.
Right.
The bank sees your transactions. The hospital sees your medical records. The insurance company sees your claims, and so on.
And nobody wants to just spill the beans to everyone else.
Exactly. And not only do they not want to give away their whole data set, they also don't want to reveal the sort of patterns or insights that are hidden within their data, right?
So we're not just talking about protecting, your individual medical record or your bank transactions. We're talking about protecting the entire category of bank transactions or medical records across all their customers.
Exactly. And that's where feature privacy comes into play. That's the really cool part of PBM-VFL.
Okay, so tell me more about feature privacy. How does it work?
So the researchers, what they did is they figured out a way to add noise to the data, but they do it in a way that protects both those individual samples and those entire feature sets. And they actually went a step further. They compared how much privacy you actually lose in this vertical setup versus the more common horizontal one.
Hold on, back up a bit for me. What exactly does it mean to lose privacy, and why would it be different in a vertical setup?
Right. So good question. Think of it like this. Whenever you're sharing information, Even if you're doing it in some kind of privacy-preserving way, there's always at least a tiny chance that someone could figure something out that they shouldn't. Now, in horizontal federated learning, where the data is spread across different individuals, it's a bit easier to kind of hide those individual details.
Okay.
But in the vertical setup, where you've got different features, but it's all about the same people, well, there's just inherently more potential for someone to kind of connect the dots and figure things out that they shouldn't.
I see. Because the more pieces of the puzzle you have, the easier it is to see the full picture.
Exactly. And the researchers behind PBM-VFL, they totally acknowledge this, and they actually prove that you do lose a little bit more privacy in the vertical setup.
Okay.
But the cool thing is that they also tell you how much you lose, and they explain exactly why it happens, you know?
So you can kind of weigh the risks and benefits.
Exactly. It's a trade-off, but the good news is that you're still getting these really strong privacy guarantees for both the individual data and those feature sets.
So they've managed to find this like really delicate balance between collaboration and privacy.
Absolutely. And that's one of the things that makes this research so cool.
Now, you mentioned earlier that the paper also looks at the model's performance. Did they actually put this algorithm to the test, or was it more theoretical?
Oh, no, they definitely put it through its paces. They tested PBM-VFL on a couple of standard image recognition datasets.
Okay.
You know, those classic benchmarks like ModelNet 10 and Safar 10 that people always use to kind of compare how well different algorithms perform.
Sure.
And the results were really good.
So it's not just a good idea on paper, it actually works in practice.
Exactly. And that's always encouraging to see.
Before we jump into some novel notions, I'd love to get your take on how this paper fits into the bigger picture of privacy-preserving machine learning. I mean, we've talked about anonymization, we've talked about differential privacy, but where does PBM-VFL fit into all of that?
Well, I think it's fair to say that PBM-VFL is kind of like an evolution of those earlier ideas. It builds on them.
Okay.
It takes the best parts like DP and MPC and combines them with this really smart noise addition mechanism to specifically address those unique challenges of protecting both sample and feature privacy in this vertical setting.
So it's like standing on the shoulders of giants,
Right.
but also taking a pretty big leap forward.
Exactly. And that's what makes this research so exciting, right? It opens up a whole world of possibilities for collaboration, but without the compromise.
All right, well, I'm definitely ready to explore some of those possibilities. So we move on to novel notions.
Let's do it. All right, so for our first novel notion, let's play a little thought experiment, right? Imagine we're trying to build a model that can predict future trends, right? Think about like financial markets or social media, maybe even climate data.
Okay, I'm following it.
And let's say you've got all these different companies or organizations, and they each have data covering different time periods, right? So one company has data from like the past decade, another has data from just the past year, and so on.
Okay, so instead of just different types of data like in our vertical setup, we're now adding this whole time element into the mix. It's like we're slicing the data horizontally through time.
You got it. Exactly. It's like temporal partitioning.
Yeah.
Now, imagine you want to train a model on all this data, but you don't want to reveal exactly when a specific event happened.
Okay, I see where you're going with this. Like,
Right.
you wouldn't want to accidentally give away the exact timing of when a stock price spiked or when a certain social media trend took off. That could be super sensitive information.
Exactly. So the question is, how do you protect that kind of temporal information while still being able to train a powerful model? And why even bother with this whole temporal partitioning thing? Why not just throw all the data together and call it a day?
Yeah, that's a good question. What's the point?
Well, think about something like climate change research, right?
Okay.
Imagine being able to train a model on climate data from all these different points in history, but without actually revealing exactly which year each data point came from. You could maybe unlock some really powerful insights into those long-term trends and help us make better predictions about the future.
Yeah, that makes sense. You could track how those climate patterns evolved over time without necessarily giving away the specific timing of, any one particular event. Like we're getting the big picture without compromising the details.
Exactly. Or think about something like social media data. You could study how language changes over time, how new trends emerge, or even how social norms have shifted, over the decades. And you could do all that without revealing the private details of any individual users.
Wow. It's kind of mind-blowing to think about all the possibilities. We could analyze historical data in totally new ways
Right.
and uncover these hidden patterns and trends, all while protecting people's privacy. But how would you actually do that? Could you adapt something like PBM-VFL to handle this temporal dimension?
That's a great question. And it would definitely require some modifications to the original algorithm. One thing you could maybe explore is something called homomorphic encryption.
Homomorphic encryption. That's a mouthful. What is that?
It's pretty wild. It's basically like a supercharged version of MPC, like MPC on steroids. It
Oh,
lets you actually perform calculations on encrypted data without ever having to decrypt it.
wait, hold on. Encrypted data. You can do math on data that's still encrypted.
Yep. That's the beauty of it. It's like you're working with this data, but it's locked in a vault the whole time.
That sounds like some next-level cryptography.
It is, but in this case, it could be really useful because it could allow those different parties to train their own little local models on their pieces of the temporally partitioned data, right? But without ever actually revealing the specific timestamps to each other or to, the central server.
So each party has their piece of the puzzle. It's all encrypted and hidden from everyone else.
Yeah.
And yet they can still somehow work together to train this global model.
Exactly. It's a pretty challenging area, but the potential benefits are huge. And this whole temporal partitioning thing is really just one example of how PBM-VFL could spark a whole new wave of innovation in privacy-preserving AI.
Yeah, that's super cool. Okay, my mind is officially blown. But before we go too far down that temporal rabbit hole, you mentioned you had another novel notion up your sleeve.
I do. And this one gets at something that's been kind of bugging me. We've been talking about how PBM-VFL protects those individual features, right? It kind of blurs out those details of whole categories of data. But what about the relationships between those categories? Like, how do you protect those?
That's a really good point. So not just protecting the individual ingredients, but also how they interact, like protecting the secret recipe.
Exactly. Even if you protect the individual features, the model might still be able to figure out something about how they're all connected, right?
Okay.
Like, imagine a model that's trained on both your health data and your financial data. Even if the specific medical diagnoses and transactions are blurred out, that model might still be able to learn that people with certain health conditions tend to have lower credit scores or something.
Yeah, that would be bad. That would be a pretty big privacy breach, even if you're not actually revealing the specific details.
Exactly. So how do you protect not just those individual features, but also those sensitive correlations between them? And how do you even define what it means to protect those correlations mathematically? That's the real challenge.
It's like we need to build a privacy shield that not only hides the image behind it, but also distorts it so you can't even tell how all the pieces fit together.
That's such a good analogy. You really nailed it. Imagine what we could do if we could actually achieve that, right? We could train models on incredibly sensitive data, things like genetic information, personal beliefs, all without revealing those underlying relationships that could be used to discriminate against people.
We could really unlock the power of AI for good without having to sacrifice that fundamental right to privacy.
Exactly. It might sound like science fiction right now,
It kind of does.
but it's a goal worth striving for. And who knows, maybe someday we'll look back at these novel notions and realize they weren't so crazy after all.
Well, I'm definitely excited to see what the future holds. Do you have any more novel notions you want to throw out there, or should we start wrapping things up?
I think we've given our listeners a lot to think about. Maybe it's time to let them come up with some novel notions of their own. What do you think?
I like that. Let's turn it over to our audience. So, listeners, we're curious, what are your novel notions? Can you think of any other cool ways to build on these ideas? Don't be shy.
Yeah, we want to hear your thoughts. Hit us up on social media. Let us know what you're thinking.
And, these novel notions, they're fun to think about, but they also really highlight the challenges and opportunities in this whole field, right?
Absolutely. It's not just about, brainstorming crazy ideas. It's about actually pushing those boundaries and making those ideas a reality.
And that's what's so great about this area of research. It's constantly evolving, right?
Yeah.
And it's driven by this, fundamental need to balance the amazing potential of AI with, everyone's right to privacy.
It's a tricky balance.
It is. But speaking of pushing boundaries, I think we got to give a shout out to the researchers behind this paper.
Yeah, for sure.
I mean, they've made a big contribution with PBM-VFL, and I'm really interested to see where this work goes from here.
Me too. And if you're interested in, digging into the nitty-gritty details, we've got a link to the full paper in the show notes.
Awesome. And hey, if you're hungry for more deep dives into, all things AI, make sure you hit that subscribe button wherever you get your podcasts.
We're putting out new episodes every single week, covering everything from natural language processing to reinforcement learning.
Computer vision, you name it, we're talking about it.
We're covering it all.
And of course, we always bring that talk tensor style.
Yeah.
The in-depth analysis, the fun discussions, and of course, those novel notions to really get you thinking.
So until next time, keep those minds curious, keep those algorithms ethical, and keep those data points nice and private.
And keep those novel notions coming. We love hearing from you.